All right, here we are again. So let's get started. So today, what we want to do is start chapter 5, which is sort of a bit of a detour into the area called probability theory. And it's a little bit different than what we've been doing because there's more concepts, let's say, than calculations. The previous chapter, the calculations were actually quite intense. But here, it's a little bit more theoretical what we're doing now. As it turns out, statistics, the entire field of statistics is ultimately based on probability theory. So this is why we need to provide this background so that what follows makes a lot more sense. So now, before we start, a couple of things. Now, you know that on Moodle, if you look there, there are problem sets waiting for you. But because it's, of course, Christmas on Friday, I don't want anybody to be doing homework on Christmas Day. So what we're going to do is this. Oh, no, we need Moodle. Hold on a second. So we're going to look at Moodle and just to remind you what's up here in Moodle. So I put a slightly updated syllabus on here. The only thing I added was the dates and times that we're meeting. These are all here. Now, the material we did in chapter 3 with the PowerPoint slides, this is actually 2 different days worth of notes. These are all the handwritten notes that I put into the PowerPoint presentation. So between these 2, that covers both days. So I called it with notes and with more notes. I didn't know what else to call it. The chapter 3 up here is the original chapter with no notes written into it. This is the notes we wrote on the first day. This is the second day. This is the spreadsheet we did yesterday, which you can download it and do whatever you want with it. If you want to learn more about Excel, for example, you might want to go in and see how everything was set up. If you want to learn how to create wonderful graphs, if you want to learn how to calculate mathematical functions, it's a very good skill to have. So you might want to look into that. Now, there is a problem set, as there will be for every chapter. So why don't we do this? Let's look at the calendar for a second. All right, so where are we? Today's the 23rd. So today's the 23rd, Wednesday. So this is it for this week. We're done with classes. Now, next week, I think I mentioned this yesterday or the day before. I knew there was a chance this might happen. I'll be coming back from a trip over the weekend, and on Monday, I'd say it's not likely that I'll be able to get back in time to do the regular live sessions. So for Monday only, what I'll do is I'll just make a recording in advance and post it on my YouTube account, which let me show it to you if you haven't tried to access it yet. Let's see. So you go to YouTube, and up here it says your account, your channel. And right here you can see there's a bunch of playlists for all my different classes. And one of them is right here. Look at it. Right there. Matt 1600 SUNY Purchase. And so all the videos are right here. Every day after we're done, I post these into the YouTube account. So you can watch them if you choose to do so. It's not necessary. But for this coming Monday, we'll just have the video instead of the actual live class. Okay, so you can sleep late on Monday if you want to. But after that, we'll be completely back to normal. So yeah, in other words, going forward, I don't think there's any more holidays. So we'll just be here Monday through Thursday at the usual time. And that will bring us through the last day. Oh, God, I need January. Hold on a second. The last day of the class is actually the 19th, which is a Tuesday. The reason why it ends on a Tuesday is because, there it is. Oh, well, now that I'm looking at this, Martin Luther King is on a Monday. I'm wondering, it's possible that that's a day off too. I'll have to look into that. But the reason why it ends not on, like on a Friday, like you would think, is because we're going to lose a couple of days for Christmas and New Year's. So but officially the last day of the class is the 19th. So it seems like we got a lot of time, but we really don't. So let's do this. Let's go back to December. Let's just agree that the third problem set, no, I shouldn't say that, the chapter 3 problem set, you can hand it in next week. Let's say, how about this? Why don't we agree that next week on Thursday, which is our last meeting of the year, actually, you can hand in the problem sets for 3 and 5. Okay. By then we will have completely covered chapter 5 as well as 3. So you can hand those both in. And then what we'll have to do when we get back is start reviewing for the first midterm. Now, of course, all the exams are being done in an online format. It will appear on Moodle, and you'll be able to just download it, and you'll be able to write out your answers. And usually what most people do is they take a picture of it with their iPhone and send it back, and that's fine as long as the quality is high enough that I can read it. So if you want to get started on that, the sample midterm is actually right here. And again, this covers chapters 3 and 5. There's a list of the topics that we would have covered by then. And then there's a bunch of fill-ins. These are short answer questions. And then there's the actual problems. And so this is meant to be a very strong, very close representation of what we'll actually be seeing on the midterm. Okay, first midterm, I should say. There's actually 2 of them. I found from experience that if I have only one midterm and final, it makes people nervous because they worry about what happens if they do poorly on one of them. So there's 2 midterms and a final, none of which are comprehensive, by the way. They're all just 1 or 2 chapters. Okay, so all right, anyway, so let's recap that real fast. Today we're going to start chapter 5, and by the 31st, which is a week from tomorrow, you should have been able to finish chapter 3 and 5 problem sets. And then on Monday, instead of having a live class, we'll just have a recording, which you can watch whenever you want to. You don't have to watch it at 10 o'clock on Monday morning, for example. And so when you don't see an invitation for Monday, don't be surprised. But then, of course, we'll pick it up again Tuesday, the 29th. Okay? So I think that's all the business that we have to talk about. Oh, wait a minute. Oh, yeah. As far as that goes, what you should do is just send it directly to one of my 2 email accounts. Let me write that down here for you somewhere. I'll put it right in the message box. There's 2 of them that you can use. The actual official purchase account, which, I use, for regular classwork, but because the Gmail is so much easier for me to work with as far as sending out invitations goes, you can use that one too. Now, having said that, first midterm, it'll be after New Year's Day. Okay. In other words, we're going to have one final class on December 31st. That following week, I'll post the midterm, or actually under the circumstances, I can post it any time, but it won't be due until after January 1st. Let's put it that way. All right. So, so I just want to mention one more thing. I would prefer that you send your homeworks or your assignments in general to my purchase account. Why? Only because of one reason, because in a normal day, I probably get 3 or 4 emails in my purchase account, and I might get 200 in my personal account. You never know. It happens. Well, maybe not 200, but the idea is that if you send it to my purchase account, they'll all be together in one convenient place for me to find them. If you send it to my Gmail account, I'll find it, but it'll just be a little harder. That's all. So as far as that goes, as far as assignments go, try to send it to my purchase account. If you forget, it's okay. I'll find it. But the other thing too is that what you can do is when you create these photographs, they create what I think sometimes it creates a JPEG, and sometimes it creates, I'm not sure what the format is called, but here's what I'd like you to do. Try to put your name in the title of your files when you send me assignments. Okay, in other words, if it comes to me and the title is something like IMG 3214, well, the problem with that is it's possible for me to not be able to figure out who sent that to me. You know what I mean? Like if it comes in a folder, that's fine. But to the extent that's possible, change the title of that document to conclude your actual name. It just makes things easier for me for organizational purposes. If you forget, that's fine. But it would be easier if it comes in and says, you know, like John Smith, page 1 or something like that would be so much easier than 30214 IMG dot whatever. Okay. So other than that, I think we're all caught up. Any other questions? Okay. So let's see. I think every single one of you is here now. Anyway, that's good. And you're all very tech savvy. You know how to use the internet. You know how all that good stuff works. You know how to use, I don't even have to ask you if you have a cell phone with a camera, do I? No. I might as well ask you if you wear shoes. I mean, come on. Everybody has that camera. Now, if you have a real scanner, though, you can use that too, because then you can turn it into a PDF format, which is nice. It's a very convenient format. If you don't, you don't. That's just the way it is. But if you have a printer in your house, there's a very good chance that it has scanning capabilities, which you know, it might come in handy. Like if you're returning documents, signed documents to somebody, legal documents, the scanning is really the way to go. I investigated that other one, the iPhone version. It turns out you have to pay for that one. So you might want to, maybe you don't have to get that one. Okay, so all right, here we go. So what is this probability theory all about? Well, before we get started, I just want to mention that probability theory is designed to help us quantify uncertainty. Now, we know that there's uncertainty everywhere you look. In fact, there's probably more uncertainty than there is certainty in this world of ours. So we'd like to assign numbers that help us understand how unlikely an event really is. So this is a very deep area of study, by the way. We're just going to scratch the surface. We're just going to do enough to get us through our statistics course. But if you were getting let's say a PhD in math, you could actually focus all of your attention on probability theory because it's that big of a field. But what I do want to mention right up front is that it is heavily based on set theory. And of course, you've all been exposed to that, but it's possibly been a while. So what I'd like to do is just quickly review sets. Basically, what we're interested in here is set algebra, so that when we see this later on, you won't say, oh my God, I don't remember how any of this stuff works. So let's start out by looking at, let's create a few sets here. Okay, so of course, this is, you recall, this is how sets are written. They're surrounded by these braces, as they're called. In math, these are called braces. Okay, and it's possible that many of you had actual braces. I don't know. Should we do a survey on that one? Oh, why not? First survey of the day, just for the fun of it. I just feel like doing a survey. Okay, yes or no? This has nothing to do with anything. I just thought it'd be fun. Let's do this. Yeah. So, 2/3 are yeses. That includes me, by the way. I had braces when I was already past 40, and let me tell you, it was not fun. It took about 3 times as long as it would have if I'd done it when I was 16. That's the problem with adult braces. It takes forever. Your mouth doesn't want to react to the braces, and it's a nightmare. It can be a nightmare, but all right, let's get back to work here. So anyway, I just want to introduce some concepts. Now, there's some symbols that we need to introduce here. I'm going to see if you recognize these. For example, if you saw this statement written down, what in the world am I doing here? What is this U thing? What is the name of that symbol? It's actually an operator.
Is that a union symbol?
Yes, it is. It's a union symbol. You know it. Now, here's the interesting question. What does it mean? Well, in English, you can think of this as being equivalent to the word or. So when I write this down, what I'm trying to do is create a new set, which consists of these two sets. In other words, I'm basically just combining them into one big new set. Okay, so you notice how all I do is put them all together. Now, you notice how the 3 appears twice in these two sets. I don't need to write it twice. It's understood that this simply refers to the list of unique elements in that set. The number of times 3 is repeated is irrelevant for this. Okay, so how about this one? Oh, that's a tricky looking one. What is that thing? Oh, don't all shout it out first. Do you not remember, or are you being shy?
I don't know what that one is. I'm gonna guess it's the opposite of union, though. Doesn't
Okay, but what's the opposite of union? All right, in this context, it is called intersection. Oh, I think somebody had it. Yes, you are right. It is intersection. Okay. So what that is, the equivalent is the English and. In fact, in some textbooks, they actually use the word or and instead of these symbols. It means I only want to include all the elements that are common to both sets. Okay, which in this case is 3. So it would be like, imagine me asking the set of all people who, let's say you're in Purchase College, the set of all English majors and the set of all history majors, where would they overlap? Those would be the double majors. Yes, you can get a double major. Did you know that? Does that change your thinking about what you want to do at school? Now that you know, are you thinking, oh my God, just think of all the majors I could have? Not only that, but you can have minors. Imagine yourself, you could stay in school for a long time if you could be like a triple major and a quintuple minor. It could be done. They'll let you do that. But anyway, now let's look at this other special case though. What if I'm doing A and C? Uh-oh, what's going on here? What elements do A and C have in common? Oh, these ads, for God's sake. What elements do A and C have in common? The answer is none. So what do we do now? We have the so-called empty set. This is a set that contains no elements. And we have a special name for this situation. A and C are, okay, mutually exclusive. That means two sets that have nothing in common. Like, for example, the red cards in a deck and the black cards in a deck. There can't be any cards that are both red and black. So therefore, those two sets are considered to be mutually exclusive. Okay, so I think that will do for now. Does everybody, you now that you've seen it again, you realize you've seen this before, right? Yeah, of course you have. It's just that it's been a while. So this is all, for the time being, this is all you need to remember. All right, now let's start the new material. Oh, okay, yes. It can be called, I'll mention that to everyone. It can be called a null set as well, because null means nothing or zero. Okay. Yeah, that's a good point. That's the thing about math. There's often multiple names that mean the same thing. So yes, I've heard them called that too, the null set. Some books call it the empty set, some call it the null set. It means the same thing. There's nothing in there. Oh, wait a minute. I just realized there's one more concept I wanted to show you before we carry on. Just one more. So using these same sets, let's say A is up. I got one more. No, you don't have to do that. You do not need to list the three twice. The set is only meant to represent how many unique elements are in there. It does not matter that there's two threes that are repeated. So we just list it as we did here. That's a good question, though. Yeah, so there's right here, you did not need to write this three twice, even though it occurs in both sets. It's enough to show that three belongs to at least one of them. Okay, now, one more thing. Actually, I can make up some new sets for this one. What if I have this, A is still 1, 2, 3. Let's say set D is 1, 2, or just 1 and 2. And then E is 3 and 4. All right, one more symbol. Let's see if you remember this one. What is this thing? What do you think? Sideways, that sideways thing. What is that all about? We have somebody who knows. Subset, that's the one. Sub. In English, this says D is a subset of A. Now, why is that? Because all elements in D are also elements in A. Okay, so in other words, you can think of it as D being completely contained with A. In fact, watch this cool diagram I'm about to show you. And if you don't remember this, I'm going to have to wonder if you were paying attention in middle school. Watch this. A contains the points 1, 2, and 3. And this is the set D, which you can see is 1 and 2. D is completely contained within A. What's the name of this type of diagram? It's a something diagram. I'll give you a hint. What's in between? When you see it, you're going to feel very ridiculous that you didn't remember. A Venn diagram. Oh, come on. It hasn't been that long. All right. Now, here's the interesting one, though. What about E and A? Is E a subset of A? No, because there's a 4 in E, which is not an A. So for that, we write E is not a subset of A. Look how easy that is. I just put a little slash through it. Okay, E is not a subset of A for the simple reason that E contains at least one element that does not belong to A. Okay, beautiful. All right, now we're ready to roll. So all of probability theory is based on the premise. Actually, let me just leave it there for a second in case you're not done. But all of probability theory is based on the premise that some type of a process or experiment is taking place, which generates outcomes which are not known in advance. So this could refer to a lot of things. Okay, so we're focusing our attention on processes or experiments in which all the possible outcomes are known in advance, but we don't know which one will actually occur. So this is a very general idea, but it turns out that it's easy to illustrate these concepts with games of chance, which many of you may have played before. For example, let's see what we have here. Spinning a roulette wheel. Okay, now everybody is familiar with the roulette wheel. What's on that wheel? Numbers. But what numbers?
Evens, odds, and colors.
It has that, yes. So if you look at the roulette wheel, it has the numbers 1 through 36, which are all either black or red. And they don't alternate, by the way. It's not the case that every other one is red or black. There's a random pattern there. And just to make sure that the casino always wins, there's also a 0 and a 00, which are green. If these weren't there, every time you played, you're basically, there's a 50-50 chance of winning. But instead, by putting those in there, they make sure they always win. Okay, so, but they're all equally likely to turn up. That's the key detail. If I spin the wheel, the chances of getting a 3 are the same as getting a 9 or a 00. They will have a probability of, what do you think? 1 out of 38, because there's 38 equally likely numbers. When we spin the wheel, we know what could come up. We do not know what does come up, though. Okay, so that could be considered an experiment. Or choosing a card from a deck. How many cards are in a deck, by the way? Let me test your memory here. Ooh, it's right in your tongue, isn't it? Tip of your tongue. 52, that's the one, yes. So just in case this comes up in our examples, why don't we have a quick review of what's going on in the deck of cards. 52 cards. There are 4 suits, which are spades, clubs, hearts, diamonds, of which these 2 are black and these 2 are red. There are also 13 what we call ranks. We have ace, 2, 3, 4, up to 9, 10. And then we have the royal cards. Whoops, almost got them out of order there. Okay, so in other words, if you run across a question which says, what's the likelihood of reaching into the deck and choosing a heart? Well, that would be 1 out of 4 because there's 4 suits, okay? Or an ace, that would be 1 out of 13 because there's 4 aces out of 52 cards, okay? So that's what the deck looks like, all right? So I guess in this day and age, people play cards on video games or on computers. I don't know, I guess they still make real cards. Certainly in the casinos, they use real cards. But anyway, a pair of dice. What numbers are on a pair? By the way, here's a fun side fact. The singular of dice is die. So if you roll one of them, it's just called a die. What numbers are on the die? 1 through 6. Okay, each one is equally likely to turn up. All right, so these are all examples of experiments. Now, we're going to assume for this next experiment, we're going to take a single die, we're going to roll it twice, and for some reason, we're only interested in whether the number turns up odd or even. It doesn't matter. Let's say we're playing a game of some kind where the only thing that matters for the payoffs is odd or even. So we only need to keep track of O or E, odd or even. Each roll of the die is considered to be a trial of this experiment. Now, what can happen when we roll a single die twice? Well, what we can do is show a diagram which illustrates this very nicely. It's called a binary tree because two things can happen every time we roll the dice. So we start out here. O or E. Obviously, O is odd, E is even. And then once we've had our first odd, the next roll can either be another odd or an even. Once we start with an even, we can then have an odd or we can have another even. All right, so these are the four outcomes that could happen. And because each die has three values that are odd and three that are even, that means that each of these outcomes is equally likely to occur. Okay, so if I roll the die twice, the chances of getting two evens is 1 out of 4. All right, same thing for these others. So we're going to do something special with these. We're going to, first we're going to abbreviate them, of course. We don't want to write out these words all the time. What we're going to do, though, is we're going to gather these together into a set, a very special set, which is called the sample space of the experiment. This is the set of all the possible outcomes of our experiment. Okay, and you can see they're all listed there. Now, it's not always the case that each one is equally likely. That just happens to be the case here. Most of the time, that's actually not the way it works. But here, we're keeping things a little simpler by choosing 4 outcomes, all of which are equally likely to occur. Okay, now, this is why we had to go through this earlier. We're going to define a very important concept here called an event. And here, the event means specifically a subset of the sample space. Okay. So suppose I define the following event. Based on the experiment we just conducted, F represents the event that at most one even number turns up, which means we're ruling out 2 even numbers. Okay. So what elements belong to the set? Now remember, F is itself a set. Well, we've got all the cases where there's one even, and here we have no evens. So because we define this as at most one even, most one even, yes, one even, which means 1 or none, you can see very clearly that F is a subset of S. And therefore, F qualifies as an event. Now, here's the interesting part of it, though. What is the probability of F? In other words, imagine that I'll win a prize if this event takes place. In other words, anything except 2 evens, I'll win a prize of some kind. What's the probability of this happening? Well, there's a couple of ways we can approach this. We could actually add up each individual probability. Since F contains the elements, the probability of F is the probability of getting EO, OE, or OO. since we already mentioned before that each of these are equally likely to occur, that means each one must have a probability of 1/4. Okay, so you have 4 equally likely events. Each one must have a probability of 1/4 or 25%. So when you add these up, you do in fact get 3/4 or 0.75 or 75%. Okay. Now, when each event is equally likely, though, we have a shortcut available to us. Now, this notation means the number of elements in set E, and this, of course, means the number of elements in set S. So this symbol, the pound sign, which is on your phone, by the way, somehow it got to be called, I don't know how and when this happened, it suddenly started to be called the hashtag. Maybe you guys are aware of the origins of this mysterious word hashtag. What exactly does it mean? In one sentence, what does hashtag actually mean? Let's see who can come up with a good explanation for a non-technical person. Or is that even possible? It's just, you just have to know it. You just have to use it. It's one of those things that you have to be under 30 to know what this means. Is that how that works? No. If I looked in a dictionary, would I find this word? No, it's meant to be a secret. Probably not. It's the young person's dictionary. Like there's a separate dictionary now, I guess, for under 30s that only they know. And this is one of those words, okay? But anyway, it's still called a pound sign, though. If you if you call somebody on the phone and you get a recording and they need your information, they'll sometimes ask you to put at the end of your number the pound sign. So it still is known as the pound sign. It's just that now it's got this other name associated with it. But anyway, so here, because we do have all equally likely outcomes, this event F could just as easily have been calculated as just simply 3 out of 4, because there's 3 elements in F and there's 4 in the entire sample space. But remember, this only works when the outcomes are equally likely. This approach always works, regardless. So this is the more general approach. This is the special case. All right, now we're going to get into some deeper waters here. All of probability theory is based on 3 formal axioms, they're called. You might remember this from high school geometry class. Does anyone here remember geometry class with fondness? Was that your favorite? No. Most people are not terribly fond of geometry. It's a special, let's say it's an acquired taste. Most people prefer the algebra and trig courses or calculus if you got to that point. Geometry is a very special area, but you might remember a lot of the fundamental results were called axioms. An axiom is simply a statement which is accepted without proof. It's the sort of the foundation of a system of logic. So we have that case here. We've got 3 axioms. Now, 2 of them, you'll probably say to yourself, you know what, this is just common sense. The third one is a little bit trickier, though. So let's take a look at these axioms. First of all, no event can have a negative probability. Okay, in other words, what would that mean? So, by the way, there's an assumption here going on that a probability of 0 means the event is impossible. A probability of 1 is understood to mean definite. In other words, this is something that will happen with certainty. Okay, so therefore, all probabilities have to fall somewhere in between. There's no such thing as a negative probability. Now, the entire sample space is defined to have a probability of 1 because when there's an experiment, something in that sample space has to occur with certainty. So in other words, if I roll the die, remember, if I roll the die twice, one of these 4 has to happen with certainty. Okay, so the entire sample space is defined to have a probability of 1. Now, here's the mysterious third one. If we have a set of events that are disjoint, this, by the way, is just another name for mutually exclusive. The probability of their union is equal to the sum of their individual probabilities. So let's say I have something like this. Okay. So any combination of these, any union of these, now remember, they have to be mutually exclusive, means we can just add them up. Okay. So those are our axioms. Now, with those being said, we can derive a lot of really important results. Okay, really important. So are we ready to see some of those really important results? Yes, we are. We're going to define the so-called rules of probability. Now, these are not all of them. These are 3 of the more important ones. The first 2 are very simple. The third one is so complicated that we have to take a detour and basically introduce some new concepts before we introduce it. So the addition rule tells us what to do or how to calculate the probability of a union. Now, here we're not assuming that the events are mutually exclusive. They might be, but they might not be. So when that happens, we can't just add them up like we did up here with the axiom, third axiom. We have to take into account any areas where they overlap. So this is the formal statement of the addition rule for any 2 events. This is always going to be true. Now, the question is why? Why must we subtract that piece? Well, let's take a look at a Venn diagram. Let's say we have 2 events, A and B, that do overlap. The intersection is here. And let's call this region 1, 2, and 3. Now, if I forgot to subtract this part, I would get this result. And guess what that means? This region is counted twice. So how do I correct for that? That would be 1 plus 2 plus 2 plus 3 minus 2. Now we're good. So now you can see why. In other words, the reason why we must subtract this intersection is to avoid counting it twice and getting the wrong answer. Actually, you know what? Let me do this. Let me change this to, that's better. Okay, now it makes more sense. So if I just add these together without subtracting the intersection, I am double counting the intersection. I can't, no, I don't want that. So therefore, this is what I do instead. All right, so let's look at some cases here. Based on the die rolling experiment, remember S equals EE, EO, OE, and OO. A represents the event that the first roll is even. That would be this case and this case. B is the event that exactly one roll is odd. That would be this case and this case. So what's the probability of getting A or B? All right, now remember, or, the English word or corresponds to union. Perfect. All right, so this is A, this is B, this is their intersection, which we will need for the addition rule, and you can see that they do both in fact contain EO. So let's use the rule. Now, by the way, the probabilities themselves, remember, these are all equally likely to occur. So all I have to do is say, that's 2 out of 4, which is a half. For B, same thing, just count them up. And then for the intersection, that would be 1/4. So now those can get plugged directly into my addition rule. And guess what I'm going to get? Okay. So there, once again, those are the 3 probabilities. And when I add them up, I'm going to wind up with, of course, 3/4.
Could you go back to slide 27, please? I just missed some
Yes.
notes.
Okay, sure. Go ahead.
Thank you.
Just let me know when you're done. Yeah, anytime I go too fast, you have to let me know. I can't tell because I'm, in the classroom, I can tell because I'm watching you, but I can't tell here.
All right, I'm good.
Okay, great.
Thank you.
Everyone else? Okay, you're welcome. So yeah, this is just what we saw here. I just wanted you to see why. And you plug them in and voila, there's your probability. Now, if you were to go ahead, now remember, let me show you this right here. Remember, A was equal to EE and EO. As an alternative, here's what you could have done. Hold on. What you could do too, and this is always an option, is literally put them together yourself into a union and then just count them. And it has to give you the same result. Okay, so there's, as is so often the case in math, there's more than one way of getting at each result. You normally, what happens is you use the one that's most convenient. So here, for example, the approach I did it right here, If A and B were very large sets, this might not work so well. But, every case is different. It's not that it wouldn't work. It's just that it would be more, more time consuming. Now, this raises an interesting question. What if A and B have no elements in common? And by the way, who remembers when two things have no elements in common, two sets have no elements in common, they're said to be two words. Let's see who remembers. What are they called? What is it? What do we describe that as? When two sets have no elements in common, they are, I'll give it the first, here we go. Mutually exclusive. Yay, that's right. Exactly. Mutually exclusive means they have nothing in common. Now, what if A and B are mutually exclusive? Does that affect my results? Good question. Well, guess what? It does. Because this intersection is the empty set. And the empty set is defined to have a probability of 0. Because that is considered to be an impossible event. This tells me that A and B cannot both be true at the same time. It would be like, imagine if my experiment consists of picking a card from a deck. A is the event that it's red. B is the event that it's black. Those are clearly mutually exclusive events because it is not possible for the card to be both red and black. Well, if that's the case, if you look at your addition rule, look what happens. In other words, remember before, this is now 0, so we don't have to bother with it. This is called the simplified addition rule. And that's so nice and simple, isn't it? We don't need to bother with this. This is the case using our Venn diagrams. They don't intersect. There's no overlapping between them. So we can just add them up. But of course, this is a special case. This only can happen when they're really mutually exclusive. They have no elements in common. Okay, so let's not forget, this means no elements in common. All right, so let's see an example of this. Here's a good one. Now, again, this is the same experiment we've been using all along. This time, though, A is the event that the first roll is even. The B is the event that the first roll is odd. And what do you notice about these two events? What is that phrase again that we keep seeing thrown around in this chapter? In other words, this is A, and this is B. A and B are mutually exclusive. So you know what that means? The probability of A or B can be calculated. By the way, as you remember from before, the number of elements in A over the number in S is 2/4 or a half. And that's why these probabilities are 1/2 and 1/2, because we can count them. The other option, of course, remember, we did say that this is also a possibility. You can use whichever one makes sense. But when they're all equally likely, you might as well take advantage of it. Okay, any way you look at it, these probabilities are a half and a half. So when you combine these into a union, what you're going to get, interestingly enough, is a probability of 1, but let's see why. Let me just go and rewrite these again. Remember, A is EE and EO. B is OE and OO. Their union is, you just bring them all together. Well, guess what? This is the entire sample space. And remember, the entire sample space, by the axioms of probability, has a probability of 1. So here's another way of approaching this problem and still getting the same answer. All right, does that work for everyone? Nice. Okay, so there's nothing going on here that's mysterious, is there? No. Good. All right, so I'm looking for confused faces. I'm not seeing any because I'm not seeing any faces, but still, if there's a problem, you can just let me know. Anyway, now we're ready for the so-called complement rule. Now, I did mention this is also a straightforward idea, but first we have to understand what the word complement actually means here. Now, do not confuse this word with this one. Ooh, that one little letter changes everything, doesn't it? What does this complement mean? Okay. This is like if you say, wow, that's a nice car you have there. It's cool, or something like that. That's a compliment. This means two things go together somehow. All right, I guess we don't need this. By the way, you may have run into this if you've ever taken a course in basic economics. So I'm gonna, that means it's time for a poll. This is a useful poll. Here we go. That includes high school, by the way. All right. This is really more out of curiosity. So, oh, this is good. I'm glad to see this. A lot of people have taken economics. Nice. The reason why I'm bringing this up is because you've run into this word before then. Let's ask this question. In economics, what does it mean when two goods are complements?
It's a complementary good.
Well, but what does that actually mean, though? There's complements if
They both add value to each other.
all right, I guess you could call it that. If they are consumed together is typically the way it's explained. That's a possibility too, that the demand for one will change when the price of the other changes. But what I specifically wanted to note is that They're consumed together. Like our classic peanut butter and jelly. Yeah. Would you ever eat a plain old jelly sandwich? No. How about a peanut butter sandwich? Maybe, but they go together so well. So here the word complement means something a little different. It's kind of the same idea. They somehow go together, except that it's more like this. Imagine if you bought a picture puzzle and it only had two pieces for some weird reason. Okay, piece one and piece two. Well, you would say that they're complements because there's no overlapping between them, but both pieces form the entire puzzle. So more formally, if we have two events whose union gives us the entire sample space, but whose intersection is empty, then we say that A and B are complements. Now, once I tell you a few examples of this, you'll say, oh, I get it right away. It's a pretty simple concept. Like, for example, the red and black cards in a deck. Why are they complements? Two reasons. Number one, all the cards have to be either red or black, but none of the cards can be both red and black. All right, here's another one. The white and black pieces on a chessboard. Complements, because again, all the pieces must be white or black, but none of them can be both. So in set theory, we formally define two events to be complements if both of these conditions are true, but it has to be both. One of them is not good enough. Okay. So now here's some notation that we're going to introduce. The complement of A, as we'll see in the next slide, is written as A with a little c. Okay, the little c stands for complement. So if you see that written down somewhere, A with a little c means a complement. All right, so are we all done with this? So we're about to define the complement rule. Now, this one requires a few steps to derive it. So since it's already after 11, why don't we have our typical morning break right about here. When we get back, I'll show you what the rule is, how it's defined, and then we'll apply it. And then we're going to take a look at the scary rule, the multiplication rule. Okay, so let's stop right here. And when we're done, we'll carry on with this rule. We'll finish it up, and then we'll get through the multiplication rule. Beautiful. All right. So I'll see you in a bit. All right, so I guess we can get back to it now. So the complement rule is actually quite straightforward. There's two equivalent ways of expressing it. The probability of A complement is 1 minus the probability of A, and this implies that the probability of A equals 1 minus the probability of A complement. It's that simple. All right, so now what I'm going to do is show you why this is happening. Okay, so the probability, let's write it like this. A, by definition, the union of A and its own complement is the entire sample space. Okay, because we know already by definition that they must add up, or their union is the entire sample space. And in addition to that, we know that they are mutually exclusive. So what that means then is that I can apply the simplified addition rule and in addition, because this union is the sample space, this probability is equal to 1. And so what you're seeing down here are simply algebraic rearrangements of this expression right here. Okay, in other words, I can subtract the probability of A complement, or A. Let's say this implies that this equals 1 minus the probability of A. It also implies that the probability of A is 1 minus the probability of A complement. So that's why this works. And you can see it's a very, very simple idea. If there's complements, the probability of one of them happening is 100% or 1. Therefore, we have this arrangement right here. So let's take a look at an example. Now, you don't have to know how to do this, by the way. You just should know how to use the rule. This is just background information so you can see where this rule is coming from. And oh, by the way, if you want to use your Venn diagrams, this is easy to visualize. Whatever A is, the rest is A complement. Okay, so the two of them take up the entire sample space and they do not overlap. All right. So how about this case? Based on the same dice rolling experiment, A is the event, the second roll is even, EE, OE, and this is, second roll is odd, EO, OO. Okay, now what do we notice about these two events? Is it true that A union B is the entire sample space? Well, let's find out. Ah, yes, it is. Okay. Is it also true that their intersection is empty? Well, they have nothing in common, so the answer is yes. So you know what that means. A and B are complements. Okay. Well, you know what? That means I can demonstrate this by showing that each individually has a probability 1/2 So in our example, remember, we're using A and B. Okay, so number A over number S is 1/2. So their union is the entire sample space, as we've already seen, and their intersection is empty. Therefore, B is A complement. And so if I need to calculate the probability of A or B, or vice versa, or just calculate one from the other, I can use either expression of this complement rule. And you can see it works out because Here, this is saying that 1 minus 1/2 must equal 1/2, and vice versa. Okay. Well, so you can see that's a very simple rule. What's following is not so simple. The so-called multiplication rule, which is used to calculate the probability of an intersection. Okay, so remember the addition rule was meant for calculating the probability of a union. The complement rule would be applied only to complements, but the multiplication rule is intended for calculating the probability that two events are both true at the same time. In other words, the probability of an intersection. Now, it's a pretty messy process. So therefore, we're going to take a step sideways, I guess, and introduce some new concepts before we introduce the multiplication rule. We need specifically to introduce some new types of probabilities. All right, but we're going to do it with a very straightforward example. Okay, 2 of the 3, as you can see here, are conditional and joint probabilities. There'll be a third as we go along. And so we're going to start by introducing what's called a joint probability table, which shows the so-called joint probabilities and what are also called marginal or unconditional probabilities. Now, the table will take a group of values and represent them based on 2 different classifications. So you'll see what I mean when we see our first example. Okay, so there'll be, for example, it could be people ranked by their age and their incomes or something along those lines. So there'll be 2 characteristics that we're studying in a table like this. All right, so let's look at this case. Now, we're going to assume that there's a school out there somewhere whose business school has students who are getting either a bachelor's degree or a master's degree, and they're all either majoring in finance, accounting, or marketing. And so here's the table. So you can see these are the college students. They're getting a bachelor's degree in business administration, BBA. These are the graduate students. They're getting a master's of business administration, which is also known as an MBA. And there's only 3 majors: finance, accounting, and marketing. Okay, now these numbers represent the number of students who fall into each of these categories. For example, this tells me that there's 130 students who are getting a bachelor's degree in finance. Or right here, this tells me there's 35 students getting their MBA in accounting. This number over here tells me there's a total of 400 students working on their bachelor's degrees. This tells me there's 100 people getting an MBA. There's 175 finance majors from both the college level and the graduate level, 215 total accounting majors, 110 marketing majors, altogether 500 students at this business school. Now, what I can do with this table is actually calculate probabilities. In fact, there's quite a few different kinds of probabilities that I could obtain from a table like this one. All right, so now if I could figure out a way to keep this visible at all times, I would do it. We'll have to do a certain amount of scrolling back and forth. But I'm hoping that it'll be clear what we're doing. So let's see. Now, so we've got the events, all right. We're going to associate letters, by the way, with these events, just to keep it simple. Now, there's one problem we do have, though. As you can see, there's 2 words that start with M, so we'll randomly assign this one a T. Okay, so remember, from now on, T means marketing. A means accounting, F means finance, B means bachelor's degree, and M means MBA. That will make it much easier to express our results. So we're going to start out by introducing a concept called a joint probability. This is the probability that two events are both true. And this is actually expressed with intersection. So let's take a look at these. What if, for example, I wanted to know the probability that a randomly chosen student is getting a bachelor's degree in finance? Let's go back to the chart for a minute. Well, look at this. Now, 130 students are in both categories. In other words, they're getting a bachelor's degree in finance. There's also 500 students in the entire business school. So in other words, the probability that a randomly chosen student is getting their bachelor's degree in finance can be written as B and F, or intersect F, and that very simply equals 130 over 500, which is 0.26. In other words, if I randomly pick somebody out of this group, there's a 26% chance that the student I've chosen is getting his or her bachelor's degree in finance. And this is what we mean by a joint probability, because two different things are both true. And you can see altogether, there are actually 6 joint probabilities that we could define from this table right here. All right, so what would be another example? All right, let's see. Let's jump down ahead here. Oh, and by the way, here in the slides, what I've done is I've showed you to make it as clear as possible that what you're looking for is the ratio of these two numbers, the number of students getting a bachelor's degree in finance divided by the total of students in the entire business school, 26%. How about the others? Like this first one is getting a bachelor's degree in accounting. Now, by the way, let me try something here. I suspect that I could copy this chart into a new slide so we don't have to keep scrolling back and forth. So let me try this. Okay, well, it worked, but I have to make some space for it. Yeah, I think we can do this. Woohoo. There we go. Oh, that's fine. So let's confirm all of these. These are the rest. There's altogether 6. So M and F means MBA in finance. That's 45 out of 500, or 9%. M&A means MBA in accounting, 35 out of 500, or 7%. MNT is MBA marketing, 20 out of 500, or 4% rather. Bachelor's degree in marketing, 90 out of 500, 18%. And then finally, bachelor's degree in accounting, 180 out of 500. We've already seen the bachelor's degree in finance is 26%. So they're all calculated in exactly the same way. Oh, wow. So that's a lot of calculations, but it's very straightforward. I think you'll agree. right, so all of these are calculated by looking for the right cell and then divided by the grand total. Okay. All right. Are we all done with this slide? Very good. Now, are there any other probabilities we can calculate? Why, yes, there are, now that you mention it. What about these totals? What's going on with those? Those are known as either marginal or unconditional probabilities. These refer to the sums, the row sums and the column sums. Okay, so we'll see a few examples in a minute. In fact, I'm going to copy this table, make it easier for us. What if I want to know that a randomly chosen student is getting a bachelor's degree, regardless of his or her major? Well, altogether, there's 400 bachelor's students. And this, by the way, is the probability just B. That's the probability of getting a bachelor's degree. Right there, regardless of the major. So we're adding up all of these three to come up with 400. The total is 500. So therefore, this probability is 80%. Okay. And again, this is known as either unconditional or marginal probability. Okay, only one thing is true. All right, are there any others here? Yes. How about choosing somebody and what's the probability that they're majoring in accounting? Oh, well, that means we're looking at all the accounting majors. It doesn't matter if they're getting a bachelor's or a master's degree. There's 215 out of 500. So the probability of A the probability of majoring in accounting is 215 43%. Okay, so again, this is a sum. Are there others? Yes. Let's just make sure, let's confirm these. I'm trying to find a way to make it as neat as I can and still fit on the slide. Okay, so for example, MBA is this one, 100 out of 500. Finance, majoring in finance is 175 out of 500. And then majoring in marketing is 110 out of 500. So altogether, there are 5 in this case, marginal or unconditional probabilities. All right, so then in the next slide, there's a summary of them all. So you're probably wondering, well, what else could we possibly do with this information? Well, we've saved the best for last, the one that we need for our multiplication rule. Okay. Oh, and so you know what I've done here? I just wanted you to see this. Here we've taken the same table and we've divided every number by 500 because that's the total. So what's happened now is that instead of having the raw original totals, you only have probabilities. Okay, so for example, you can read it right off the chart now. The probability of BNF getting a bachelor's degree in finance is 26%. You don't have to do any dividing. So this chart has the advantage that all these numbers are already probabilities. The drawback, though, is that we don't know the actual totals. In other words, if I need to know the actual number of students in this category, I won't find it on this table. Okay, all I know is that 26% of the total is getting a bachelor's degree in finance. But if I need the actual number, I need the original table, which of course tells me that that would be 130. So we can use either one of these to calculate our probabilities. This one is a little bit quicker if all we're interested in is probabilities. But you can see it tells us the same probabilities. It doesn't tell us the raw totals, but we do have our probabilities. If that's all we care about, then this might be the way to go. All right. Now, like I said, we've saved the best for last. We're going to look at what are called conditional probabilities. Now, this is a very interesting concept because with these probabilities, they depend on whether or not another event has actually occurred. So in other words, let's say the probability here, and just making an example up off the top of my head, what is the probability of going to the movies given that it's raining? Well, I think you'll agree that the probability of going to the movies does depend to a certain degree on the weather. Obviously, if the weather's nasty out, you're more likely to go to the movies than do something else. So the probability of going to the movies is different than the probability of going to the movies given that it is raining out. So here we're looking at probabilities that depend on whether or not something else is happening. And they're known as conditional probabilities. Now, it sounds very complicated. When you see an example, you'll say, oh, that's not so bad. So let's take a look at this one. Now, suppose instead of choosing a student at random from the student body, what if I pick a marketing major at random? And I want to know the probability that that student is getting a bachelor's degree. Now, you see how this is completely different from what we did before. Before, we were picking somebody from the entire business school. It could have been anyone. But now we know for a fact that this person is majoring in marketing. So what we're going to do is get this chart so we can remind ourselves how this works. Let's see how tightly I can squeeze this in here. Uh-oh. It doesn't want to be squeezed any further. That's right, I can fix this. Okay, so the probability that a randomly chosen student is majoring in marketing, given that he or she is pursuing a bachelor's degree, what we have to do is just think, well, we're only considering these students. Let's see. Yes. Of which these are the only ones that are getting their marketing degree. So what I'm looking for here is the ratio of 0.18 to 0.80. All right, so we know that the joint probability of getting a bachelor's degree in marketing is 0.18, right there. But the total probability of getting a bachelor's degree is 0.80. So therefore, what we're looking for is the ratio of these two probabilities, which is 0.225 or 22.5%. And if you notice, we've introduced some important new notation here. This little bar here represents, or in English, is given that. This is a conditional probability and it's formally defined as the joint probability of T and B, or B and T, it means the same thing, over the probability of B. And so therefore, we can look these numbers up in our chart. Remember, this is 0.18 from here, and we're here. And this 0.80 is the probability of getting a bachelor's degree. So it's the ratio of these two numbers. And that turns out to be 22.5% or 0.225. Now, if we didn't know that this student was getting a bachelor's degree, we would have just been able to say, well, what's the probability that this person is majoring in marketing? And that would have been 0.22 out of 1 or 0.22. So it's not the same, is it? No, they're very different ideas. Okay, so this is where it's getting a little intense, I know. There's several different conditional probabilities that we can calculate from this table, but they're all done in exactly the same way. The bottom line is that whatever it is, in the numerator, you have the joint probability of these two events. In the denominator, you have the probability of this event. Okay, so it's a joint probability of these two events in the numerator, the unconditional probability of this event in the denominator. It's always the same. So if you remember that, you'll never have a problem with conditional probabilities. All right, so I know you're skeptical. It looks scary, but it's not. It just takes a little practice. Beautiful. So let's do another one. How about this one? A randomly chosen student is pursuing an MBA given that he or she is majoring in accounting. In other words, I've randomly picked an accounting major and I want to know the probability that this person is getting an MBA. So as far as the notation is concerned, whatever we know goes here. Okay, we know that this is an accounting major. With that information in hand, we want to know the probability that they're getting an MBA. Okay, so that's how we start. We want to make sure we're using the notation properly. M given A. Okay, and don't forget that little bar means given that. So what do we know? That goes in the denominator. What do we not know? That goes in the numerator. All right, now we of course apply our formula, which is, oh, let me write it out here. So once again, we always have a joint probability in the numerator, M and A, and then this goes in the denominator. By the way, I just want to point out, in case I didn't mention it before, when it comes to unions and intersections, the order in which we write this doesn't actually matter. This means the same thing. It's like addition. There's no distinction made between 3 plus 5 and 5 plus 3. The same thing is true with intersections and unions. So in other words, those both represent the same information. Just in case you weren't sure. Well, what are these numbers on our chart? Well, here's M. Sorry, this is M and A. And here's the probability of A down here. So this ratio would therefore be 0.07 over 0.43, which is approximately 16.3%. Okay, so roughly 1 out of 6 accounting majors is getting their MBA. The rest are getting their bachelor's degree. Okay, so you can go through and calculate all of them if you want to. All conditional probabilities are exactly calculated the same way. Now, with all that being said, all of that background now was just building up to this one rule, the multiplication rule, which as it turns out can actually be written in 2 different equivalent ways. But both of them require these so-called conditional probabilities. So let's see how this works. All right, this is one way of expressing the multiplication rule, and you can see it is in fact the product or the probability of a joint probability and this is of course a conditional probability. And this is an unconditional probability. Now, I'm going to show you in the next, in fact, I'm going to copy this here so you can see them side by side. It turns out that you can do this either way. Now, which one you choose will depend on what kind of information you actually have, but both of these represent the same thing. This is our so-called multiplication rule. And you can see it is by far the most complicated of our 3 rules. Oh, yes, it is. All right. So I'll give you a minute to catch up. And by the way, if you're, when you look at this carefully, you'll see what's different in these 2 cases is what information you're given. So in other words, in this first case, you're given A and you're looking for this probability. In the second case, you're given B. That's why there's 2 different versions of this rule, because you could be given either of these 2 pieces of information before you do the calculations. All right. So now these examples are fairly complicated. So now, since it's pushing 12 o'clock, rather than rush through some examples, I know that this was a very complicated topic. So what I think we might want to do is stop right about here and so get a chance to recover. Now, remember that the chapter 3 problem set isn't due until next week, the Thursday, the 31st. And at the same time, since we're getting very close to the end of chapter 5 here, you'll also be able to hand in the chapter 5 problem set. So you've got more than 1 week to get them both done, even allowing for the fact that it's Christmas time. So in the meantime, what you should probably do is read through these slides and make sure you understand what we've been doing. And also don't forget on Monday, and I'll send you a reminder of this, rather than having a live class, we'll have a recording of, what comes next, obviously. And then on that Tuesday, we'll just go right back to normal and we'll have our usual 10 o'clock classes. Okay. So in the meantime, I hope you all have a great Christmas and I'll see you all next week. All right.
Merry Christmas.
Merry Christmas.
Wait, Professor, I still like, if you don't mind, do you mind just repeating the important dates that we have? So I know next week, like next today.
Yes. So here's the dates. Next Monday, we'll have a recording instead of a lecture.
Okay. I'm sorry, I'm just writing this down.
Right. And on the 31st, you should hand in the problem sets for chapters 3 and 5.
Problem set 3 and 5.
Correct. Now, there's nothing to stop you from doing it earlier, but they won't actually be formally due until the 31st. In
Okay.
fact, you might want to work on them now, since, Christmas is not
Yeah,
till Friday.
I was gonna start probably problem set 3 after class.
Okay. Well, it's still fresh in your memory. And remember that, the slides are on Moodle, along with my handwritten notes. And the recordings are on my YouTube channel if you want to watch them again, if you've missed something.
Yeah.
And, you can always send me emails. Even if I'm traveling, I can still get to my emails. And then as far as the exam goes, that would have to wait till after New Year's Day.
Okay. So just to like clarify, how exactly do the exams work? Like we're all like on a Zoom call and you're like watching us, or like how exactly is that?
No, you just do it at home and you take pictures of it.
Okay.
I trust you. Don't worry.
Yeah. No, I was just curious because I know like my other classes, like we would have like we would just be on Zoom and just
Well, you know what? This material is so complicated. I don't need to watch you anyway.
yeah. My thing is, I also did send you an email last night regarding like I was in class today because something came up, and
I didn't see that. All right. So you missed. Oh, that's right. I mean,
yeah, so I'm just gonna watch the
yes,
through YouTube.
right. It's right here, and I showed it before. It is right, and it's just literally a recording of what we did. The quality of the recordings is actually pretty good. And so it's right here. You just have to remember, look under my name and go to playlists. It's not all jumbled together because otherwise you'd never find it. And right there's us.
Got it.
In fact, I accidentally turned one of them on right now. You see, it's just what we did yesterday.
Got it.
Oh, come on, let's get to the good
First class
stuff.
Back is gonna be Tuesday the 29th, right?
So yes, there it is. All right. And so today, now it takes a while for these to be ready. So, the one we're doing right now won't be ready for a little bit, but the first two are definitely there.
Okay, got it.
All right. So
All right.
I guess we'll see you next week.
Yep, next Tuesday, right? The 29th.
Yes.
All right, thank you so much.
Okay, bye.
Thank you.
Dr. Anderson?
Yes.
Yeah, hi. I have a quick question.
Sure.
It's in regards to one of the first slides you showed.
Oh, yeah.
Slide 8.
All right, let me go get it. That's good. We want to make sure you did not miss anything. Whoa. There we go.
I think it's one more up. Let me see. It's about the oh wait, you added some more. It's about the subset, the event subset.
Oh, yes. Events are defined as subsets of the sample space.
There it is. So if you go down 2 more slides. Okay, there it is. So F, you said that at most one event number turns.
That's right.
Not
In other
right,
words,
one
either
even
zero,
number.
it's the same thing as saying either 0 or 1 even number it turns out.
Okay, so if you go down one more slide. Okay, so I see that F, you have one even and one odd and one even, and then two odds. So for this case, why are you including the two odds?
Oh, because at most 1 means either 1 even or no evens.
At most one even.
Right. It's
So
like,
it does.
it's imagine
Yeah.
that I told you go to the store and your mother says, here's a $20 bill. You can spend at most $20. That means you can spend $20 or less. So here at most 1 means 1 even number or less than 1, which would be 0 in this case.
Okay, so in the for example, in I was checking the problem set, right?
Yeah.
You said, so you said event one is if at least one heads
Oh,
turns up.
At least 1 is the other way around. That means 1 or more.
Okay, so for this case, it will be, you know, we'll get four probabilities: double head, heads and tails, tails and tails. So for this subset will be all the events that at least have one head.
That's right. Exactly. 1 head or more.
Okay. All right. I see. I think I get it now. One other quick question. So I'm gonna try to do this problem set, but I don't know. I don't feel 100% confident. Is there any way you can provide feedback if I send it to you before submitting it?
Yeah. Just,
Okay,
put in the
great.
email, just say, make it clear to me that this is not your final result. Just say, could you look
Okay.
at these and see how I'm doing?
Perfect.
And I
Thank
can,
you so much.
Sure.
Thank
Absolutely.
you so much, Dr. Anderson.
Okay.
I'll see you on Tuesday. Merry
All right, see you
Christmas.
then. Merry Christmas. All right. Bye.